So, looking here, redox. We're covering redox again because at the beginning of the year we went through this briefly. And the next part of the unit is electrochemistry, and electrochemistry is basically all the reactions are redox reactions, and you have electrons, of course, transferring, and we're going to be looking at the cells created, which is in essence what forms the batteries that we use in our everyday lives. Those chemicals in there create a flow of electrons, and that's where we get our power from. So we need to make sure we can balance and we can look at charges and know the basics before we get full on into electrochemistry. Now, electrochemistry, I find it to be a lot more difficult. I thought, you might think the second part of thermo is hard, but in terms of electro, because it's not something you've ever really seen before, may seem a little bit more difficult. So definitely, give it your all for this section of the unit. So redox, reactions involving a transfer of one or more electrons, which means changes in oxidation states. So that's the oxidation states are those charges that we'll be assigning. Okay. So what is oxidation again? Anybody remember? The loss of electrons, good. And because redox is a partnership, reduction must gain electrons. So we have our nice little sayings here to help us remember. I prefer oil rig, but you're welcome to like Leo Gurr. Oil rig, oil oxidation is loss, and rig reduction is gain. And of course we're referring to electrons there. Leo Gurr, the lion says Gurr. Loss of electrons is oxidation. Gain of electrons is reduction. You can remember it either way, whichever way you would like to do that. It's fine with me. Yes? I don't know. Your guess is as good as mine. I have not been to Africa on the safari, so. Now, we're going to get into this in detail, but our example up here, the iron 3 oxide plus aluminum, okay? So, assigning our charges, okay? And that's why a lot of people find this section difficult, because you have to be really good with knowing how to assign charges. So we're looking at the ones that actually change their charge here. So Fe is going from a +3 to a 0, and aluminum is starting at 0 and going to a +3. And technically, when assigning oxidation states, this is where you write the charge first and then the number. It's a little nuance you might see, whereas if we were writing aluminum with its formal charge, we usually put the number and then the charge. So this would be like an aluminum ion versus just assigning it an oxidation number, and the oxidation numbers really are for trying to keep track of where the electrons are going. Okay? Or did you gain them, did you lose them? The oxidative oxidation number is really looking for where and keeping track of electrons. So there's a little bit of a difference. This is more of the formal charge way. And we'll be talking about formal charges in Unit 7. Versus just assigning oxidation numbers, usually write the plus or minus first and then the number. Okay? So one little extra little tidbit there. Okay, any questions? Going on to the rules. So here comes the assigning rules. And a lot of them you should be familiar with. I'll go through the examples of each one after you've had a chance to write them down. Okay, so rules for assigning oxidation numbers. This is where a lot of people get tripped up because they forget on the elements. The elements are neutral, so they get zeros. And that includes your diatomics. So don't forget your Dr. Brinkelhoff or your 7 rule, and make sure you always assign diatomics zeros as well. Okay? Now, when it says oxidation state of a monatomic element, in some of the equations that you balance, you might just see, like, you'll see this one a lot. Manganese 2, okay? That means its oxidation number is obviously +2. Okay, so if you see elements like that, then you know that's the oxidation number of that. And typically, what you'll find is most of them follow their group number charge, like alkali metals are +1. Alkaline earth metals are going to be +2. Aluminum's always +3. Silver's always +1. Zinc's always +2. All the ones that have one charge that aren't moms are going to follow that charge. The cations are. The anions are the ones that are a little bit different. If they're in the second part of the compound, they usually follow their anion charge. But if they are in the first part of the compound, then you need to do some calculation and figure out what the charge is going to be. Oxygen's always -2, except for when it's in a peroxide. Okay, and peroxides are very rare. We're not working with them a whole lot, but remember, peroxide is O2 2-, so really each oxygen's only worth a -1 there. Okay. H is +1 in covalent compounds and -1 for hydrides. Hydrides means they're in ionic compounds with a metal. Some of the oxidation states are equal to 0 when it's a neutral compound, and then the sum of the oxidation states are the charge of the ion, and that's for referring to the polyatomic, so you would add it up to that charge. So like carbonates, CO3, so, and it's a 2-, so when you add it up, it should all equal -2 there, okay? So now, you're going to practice. Go ahead and start assigning oxidation numbers to these different elements in the compounds. Okay? So let's take a look here. Oxygen is -2. Now, we want the actual number assigned to the element, not the total number. So you can use the totals to figure them out, but you know, here I don't want -4 for oxygen because there's 2 of them. I only want that oxygen's charge is carrying a -2. Its oxidation state is a -2 here. So in that case, that means carbon has to be a +4. Then here for nitrate, oxygen is still -2, but remember this one has to add up to -1. So that means the nitrogen is going to be a +5. All right, for sulfuric, okay, we're going to have -2 for the oxygen. Hydrogen, by the rule, says it's going to be +1. And then the sulfur must be a +6. Down here, we've already done this one. Iron is +3. Oxygen is -2. This is an interesting one. The oxygen is still a -2. But the iron, in this case, is a +8/3. Now, you're like, why do they have that? That's weird. It's a fraction. In essence, basically, what's going on in this particular compound, in the lattice structure, it really is more representative of 2 different things bonded together. You have some irons in here that are +2s. You have some irons in here that are +3s in the lattice structure of the crystal, okay, in the bonding. So it's sort of like coming up with an average of the 2 together in the structure, okay? And you're going to find that this also fractional oxidation numbers and states happens in the hydrocarbons as well, and particularly in combustion reactions. So like for instance, if you have like C8H18, Okay? The hydrogens are +1s, okay? But the carbons are going to be what? Minus, is it 9/4 if it's reduced? Okay? So, and the way that these work for the hydrocarbons, because if we were to draw out the structural formulas, you would see it be CH3, then CH2, attached in the chain like so. Okay, and this would go on all the way down till we had our 8 carbons in there, and the end group would be also a CH3 group, just like this first one over here. But in this case, the carbon is a -3, the carbons are -2s in the middle. So it's sort of like averaging those together. And you won't see them very often, but that's why we can have fractions for oxidation numbers. And it is really more representative of trying to keep track of the electrons here. Okay. Now for oxidation and reduction. Okay. The element that loses the electrons we say is oxidized. That's one of the key words. Or we can call it the reducing agent. And in your book, they also call it the reductant. So you might see that word in your problem set, the reductant. Okay? When something's oxidized, it loses electrons. And since this is a partnership, that means another element has to gain those electrons. So the one being oxidized is actually causing the reduction of something else. So that's why we call it the reducing agent. And they are reversed, opposite of each other. And vice versa is also true. If we have something being reduced, that means an element is taking electrons away from another element. So it's causing the oxidation of another element. So we would call it the oxidizing agent if it was being reduced. Now, in your problem set, you might see this word. They call it an oxidant. And an oxidant is the same thing as an oxidizing agent. Okay? So here, in this example, sodium is going to +1. So it is being oxidized, and therefore it would be the reducing agent. Okay? So this is being oxidized, and it would be the reducing agent. Now for the chlorine, Cl2 starts at 0, and it's going to go to -1. So therefore, it is being reduced. And so it would be the oxidizing agent. Okay, just for a quick little example there, you're now going to work some on your own here. One other little nuance about the agents, the reducing agent and oxidizing agent. They're always going to be one of the reactants. They're going to be on the reactant side. And in this particular case, we have 2 elements. But if the oxidizing agent is in a compound, we label the entire compound to being the oxidizing agent, not just the individual element. So that's kind of something different than what was probably taught last year. That we would label the entire compound that is the reactant, even though only one of the elements in it is actually doing the oxidizing. Okay, so go ahead and try the next couple. Here, labeling everything. Okay, so the best way to do this is assign the numbers. Okay, then it's easier to tell. Fe is going from 0 to +3, so it's being oxidized. And therefore, this is going to be your reducing agent. And the oxygen is going from 0 to -2, and it's being reduced. So it's going to be your oxidizing agent. Down here, same charges, +3, -2. This is now going to be a +2, -2, and 0, and +4, -2. So the carbon is going from +2 to +4, so it is being oxidized. But when you're labeling the agent, this entire thing, the carbon monoxide, is your reducing agent, not just the element. Okay? And then iron goes from +3 to 0. So it's being reduced. And therefore, the iron 3 oxide over here is the oxidizing agent, the entire compound. Last but not least, down here, we have +7, -2, -2. This is what? +5, +1. This is now +7, -2, +1, -2, and +2. So the sulfur is going from +5 to +7. It is being oxidized. Therefore, the SO3 -1 is the reducing agent. The manganese +7 to +2 is being reduced. But permanganate, this entire compound here, is going to be your oxidizing agent. Question? H plus is +1. It carries its charge on here, yes. Yes. Remember I said the monatomic one, that was that second rule. If it has a charge on it, it carries that charge. Yes. That's its oxidation state. Okay. Any other questions? Okay. Yes? Good? All right, starting to balance, right? We're on to balancing. Rules for balancing. Good times. We're going to write down the rules first, and then we're going to work through the example, and you're going to try a few on your own. So, now step 1 is write separate reduction and oxidation half reactions. Okay? You're going to write out the half reactions. For each half reaction, you have to do a series of steps. You first need to balance any of the elements besides hydrogen and oxygen. So everything else you need to make sure is balanced before you do anything with the hydrogen or oxygen. If all your other elements are balanced, now you start with oxygen first. And you must balance it using water. Okay? Now, the reason why is because we are in acidic solution here. Acidic solution means we have what in it? We have hydrogen ions, so we're going to have some H pluses in there floating around. What else is going to be in the solution? What else should be in the solution besides H pluses? In the solution, making it liquidy. Water, thank you. Okay, I'm going for water. So we're going to have water and H pluses in there that are going to be involved. That's why you're going to be able to tell on a lot of your questions if it says this reaction takes place in acidic solution or basic solution. That is a huge hint that it's redox balancing. And redox balancing is different than regular balancing. So if you see that, this takes place in acidic solution or in dilute acidic solution or something like that, you're going to be doing redox balancing. Okay? So keep that in mind. So after we have balanced our regular atoms besides H and O. Then we balance the O's using waters. And then because the waters are going to throw off the H's, and then you're going to put H pluses on the other side to balance out the new H's that you added through the water. After that is done, you're going to look at the charges and figure out the electrons. Okay? So you're going to balance charge, and you're going to do it through electrons. And that's the extra step here that's different from regular balancing, is we have to make sure the electrons are equal for both half reactions so they cancel out. The electrons have to balance. That's what's important here. Okay? So that's only step 1 and 2, right? So let's continue on. Do we all get step 1 and 2 down? All right. Now, most of the time you're going to see electrons for each half reaction are not always going to be equal. So you're going to need to multiply them by integers in order to get like a common factor so you get equal amounts of electrons. So you will multiply by integer to equalize electron number in each half reaction. Once the electrons are equal, you can merge them together and add them. So you would add the half reactions. And then at the end, you will do canceling and checking charges and making sure everything is balanced. So that will be the last few steps to do. So these take a while. They do have, multiple steps to them. You do need to make sure that you take the time to learn the steps. And your next problem set, we won't have a lot of the information yet till next week because we won't do the electro notes till next week. But you can start a few of the problems because the beginning of the problem set will have some balancing redox. Okay? So you can do a couple of those while you're working on your lab. Okay? Okay, so let's go ahead and take a look at our example here. And we're going to go ahead and do the balancing. We have Al plus permanganate. And we have this complex ion with the hydroxides. It's a complex ion. You might see some random weird ones in your reactions, but they still work. All right, so if I'm going to break this up into the two half reactions, obviously I'm going to take my Al, and it's going to break up with what? Which of the products should it go with? This one, right? Because they both have the same elements in them. Oops, what am I doing? Never mind. All right, let's try this again. Al arrow. There we go. That's our first half reaction. Okay, I'm going to hopefully write this one a little bit smaller over here now. So this one's going to be permanganate going to the manganese 4 oxide. Okay, so broke them up into their half reactions. Now we need to check out, are the aluminums balanced?
Yeah.
Are the manganese balanced?
Yeah.
Okay, now we can move on to which one?
Those.
O's. We need to do the O's next. So I'm going to add how many waters?
4.
4 waters. Okay, and for this guy, how many waters? 2 waters. Okay, so we added and balanced out our O's. What's the next step? H's. Now we're going to add in our H's. So here we have 4 H's, and this side has 8 H's. So we should put in 4 H pluses over here. And for this one, we have 4 H's. So I'm going to kind of draw a line here so we know which side is which. So then this one's going to get 4 H's right over here. So far, so good. Are we all at this point? What's the next step? What's the next step? Charges. Now, do not look at the individual elements. That takes way too long. Just look at the sides here. These guys over here, both don't have a charge on them, so this side is just 0, neutral. Over here, you're looking at the overall charges. This is a -1 here, and these are 4 of +1s. So this side should end up being what? +3. +3. Yes. So I need 3 electrons to make this one work. Where do I put my electrons?
On the right. The right.
0 to +3, the electrons must go over here. So I'm sticking them up top because I can't fit them in. But they are on the product side. Okay, let's look at this one over here. We have 4 H pluses and a -1 here. So that side's going to start out as a +3. Okay, over here, both of these guys do not have any charges. So this would be a 0, right?
Mm-hmm.
So where do our electrons need to go to make it go from +3 to 0? Reactants. So we're going to put our +3 electrons over here. This one actually works out nicely because the electrons are already balanced. Usually, though, one side might have 2 and the other side might have 5 or something like that, and that's when you have to use those multiplying factors. So you're going to have an example like that where you need to do the multiplying. Usually it doesn't happen this way where they are both the same initially. Okay?
Would you multiply the whole equations?
Yes. You would multiply the entire half reaction by that multiplying factor. Okay? To make the electrons work. Now we can cancel and merge. So electrons go bye-bye because they're equal. So over here, reactant side I have 4 H's on this side. On this product side I have 4 H's. So they can cancel. They go bye-bye. And our waters. This side has 2 right here. This side has 4. So the side with the 2 completely cancels. And we need to make this one now what? 2 waters. Okay? Is there any canceling left to go? So let's just merge them together now. I'll give us some more room here. So I have 2 waters plus aluminum plus permanganate, giving us the aluminum hydroxide complex ion plus manganese 4 oxide, and is that it? Everything else canceled, right?
Yes.
Okay, so this is your overall balance now reaction. So you're going to do the next 2 on your own. However, there is kind of a little bit of a trick to the second one, because you'll see something that seems out of place, and there are 2 ways you can deal with that. So be careful about what you're going to do with that sodium, and you can talk to your table mates and try to come up with some kind of solution.
You'll ignore it.
We don't need to do anything with the
Okay, so you can check yours here.
No, wait. Not 15. 59.
Yeah, someone passed out when I was medical.
No, I know you're right.
Physics. Next time I got it. Artery. Oh no. It was more breathing, like it's like breathing. Hey, let me see. Standing burns more calories. Did you get a crayon? Did you get a crayon? I think we can all say
Okay, so check number one. Let's check your answer.
I have a question.
For number one, now once again on number two, you could have balanced it with or without the sodium. If you took out the sodium though, you would have, if you take out the sodium here, you need to make this BiO3 with a -1 charge. If you keep the sodium in, you don't take out the sodium, then you need to make sure you add in sodium pluses because the sodiums are technically spectating in there, and this is the way they add the little tricky ones in there by throwing something in there where they expect you to know that sodium's spectating. Okay? So either way, you could have set that one up. Okay? So what it should have eventually worked out to being, I will write them both up there if you did it either way.
I was really hungry.
So that was one option. Or the other way you could have had it. So technically you could have just canceled this part off and that part off. But then you would have had to make this a -1 in your final. Okay? We just have one other quick little thing to go over, which is balancing it when you are doing basic solutions. You do the same thing with the acidic, but there is an extra added step at the end. Okay? So let's write those down. You're going to balance it as an acid first, just like it's an acidic solution. At the end, though, after you've completely balanced and merged it and got it to where it's supposed to be if it were an acidic solution, you have to add OHs that equal any of the H's to both sides. So if, say, your reactant side had 8 H pluses, then you would add 8 OHs to both sides. And those OHs will combine with the H pluses on the one side and form waters. And then you have to do some extra canceling. We're going to do an example in just a minute that shows this. So you can go ahead after you write down your rules, start getting it set up as you were to balance it in an acidic solution, get to that point, and then we'll add on the OHs and show you how to do that. So go ahead and write these down and then start on the example, balance it in an acidic solution, get it to that point, and we will add on our OHs. Since basic solution means it's going to have hydroxide involved. So yes, you can change that to balance as in acidic solution. As it's in acidic solution. Just like it would be if it was in acidic solution. You're balancing it exactly the same way first. That's what we're going for there. Okay, so let's look here. So we should have gotten to this point using the regular balancing in acidic solution. Okay? And then we're going to do the final steps to get it to the basic solution. All right, so everybody's here at this point. Got to the acidic solution. Now, to make it in basic solution, this side has the H pluses on it. Okay, and there are 8 of them. So we need to add 8 OHs. What we do to the one side, we must do to the other side. So this side also gets 8 OHs. Now the OHs and the H pluses combine to form 8 waters. Okay, so those two are going to merge into water. Okay, now there's one last cancellation that must happen because there's 4 waters over here. The 4 waters are going to go, and the 8 waters now are going to reduce to 4 waters.
Just leave the 8 OH.
Yes, and then you will, in your final answer, the final answer, be 3 Cu plus 4 waters plus the 2 nitrates. Give you 3 copper 2s, 2 nitrogen monoxides, and 8 hydroxides. So the hydroxides are in there telling you that obviously it's in basic solution. So you do everything the same and then you add in the hydroxides at the end. So that's basic gist of how to do the basic solution balancing. Okay?